Welcome to the next class in this unit. We are on to looking at the chain rule today, having already covered the product rule and the quotient rule. This is the most challenging of our derivative rules, so we're going to take a little bit of time here and make sure we do plenty of examples, and we'll get right into it. So in the IB syllabus, we are completing section SL 5.6, the chain rule for composite functions. And if you don't remember what a composite function is, this is this f open circle g, sometimes called fog. I will always tell my students to rewrite this so it actually looks like a composition. I like to see that g of x function inside the f, or vice versa if it's the other way around. So the kind of problems this rule will allow us to differentiate or take the derivative of, it's functions inside of other functions. So things like 3x squared plus 5x plus 2 all raised to the 7. So just using the power rule, I'd have to multiply all that algebra out and then apply the power rule to take the derivative. Well, that would take me a really, really long time, and I'm sure I'd make lots and lots of math errors. So we want a shortcut to do that in one or two lines here, and that's where the chain rule will step up for us. So if we think of this in terms of functions, like an f of g of x, an inner and an outer function, for this first example, the inner function, the g of x, that would be the 3x squared plus 5x plus 2, and the f of x, the outer function, that would just be raising the input to the power 7, so we would call that x to the 7. Okay? This is mostly Algebra 2 review, so if you haven't done this in a while, find a good video online where they'll go over compositions for you. For the second function, this y equals sine 3x, there is no way to get around that composition. There's no algebra we can do to simplify that to use derivative rules we've already seen. So that we definitely need a chain rule for, which we'll learn today. The inner function here is the g of x, that would be the 3x, and the outer function here is the trig function, the sine, and again, if we uncompose it, that would just be sine x. Now, I find the version of the chain rule given in the formula booklet not super useful, so we're going to look at a fun way to kind of memorize this and do it enough that hopefully we don't need this rule. Okay? So they say y equals g of u and u equals f of x. Well, if we build that composition back together, we get y equals g of f of x. So we can put this back like a composition. The part that doesn't help us is this piece over here, dy dx equals dy du times du dx. Okay? Now you can do the chain rule this way. It's not wrong. It's just not the way I personally like to teach it. Okay? So I like to do a different notation for the chain rule. Okay? I would do y primed is equal to g primed of f of x times g primed of x. Okay, and we can put this in words underneath to help us understand what's going on here. Okay, so I'm going to use a bunch of colors just to help explain this. Okay? So let's look at this first chunk underlined in purple. Okay, what is going on here in words? Okay, g prime, that is the derivative. Okay, so in words, it's the derivative of the outer function. Based on the definition in this red box, g of x was the outer function. Okay? It's the derivative of that, so derivative of outer, and we're going to say evaluated at the inner function. Okay, so essentially take the derivative of the outside, but leave the inside alone. Okay? So this piece of words, this section makes up that purple piece, okay? And then the part I'm underlining in yellow, what is that in words? Well, there's a multiplication, and then it's g primed of x. So that is derivative of the inner function. So this chain rule breaks down the derivative of the outer, leave the inside alone, times the derivative of the inner, multiplied on the end. And if you're still struggling with this, I'm going to link a video in the description to a YouTube video that I will show in my class from a guy who goes by the name of Professor X Squared, and I highly recommend you watch at least the first kind of 6 to 8 minutes of that video, because he will go through and he will even rename this chain rule. Okay? He'll go ahead and call it the glob rule. So that's the idea I'm going to go through, so if none of this globbing makes any sense, please check out that video in the description to get caught up. So Professor X Squared tells us we can use the glob rule instead of the chain rule. It's really just a different version. And we essentially put this green glob around our inner function. So this is what we call our glob. And he tells us the derivative of a glob is just the derivative of the outer. So the outer here for me is 7. I do 7 globs, and then I drop that power down to 6 using my power rule. Right? And then I can just fill in my regular glob right here, 3x squared plus 5x plus 2. But the chain part of the chain rule says I need to multiply by the derivative of that glob. Right? So d dx means derivative, and I'm taking the derivative of 3x squared plus 5x plus 2. Okay? Now the globs here are just a fun kind of unique way to remember what's going on here. We're going to get to the point where we don't need to draw them, but for now we can take the derivative of this quadratic and chain it on the end here. That is 6x plus 5, and we'll hold it together in a parenthesis just so it all multiplies there. And that's it. That's the derivative of that composite function. Okay? And we did it using the chain rule, or as Professor X squared likes to call it, the glob rule. We'll try it again on this sine 3x. Okay? We're asked to find y prime. So we'll glob up our inner function. That's the 3x. And like he says in the video, the derivative of sine of a glob, we take the derivative of the outer, the part not in the glob. So the derivative of sine we know is cosine. We leave the glob in here alone, so that 3x stays the same. I'll draw the glob again. This is probably the last time I'll draw it. And then we multiply this by the derivative of what's in that glob. So the derivative of 3x, that's just 3. Okay? Now we can clean this function up by putting that 3 in front so that we don't have to use an extra dot for multiplication or even a parenthesis. And that's it. That's our derivative. Derivative of sine 3x is 3 cosine 3x. Now you're always going to forget this 3 in front just because you're not very practiced at this. But the more examples you do, the more you'll get used to this chain rule idea. Turning the page, we come on to some shortcuts, and these shortcuts really help us when we have that glob or that inner function that's linear. Okay, it could be kx plus b in terms of being linear, k as a constant, or it could just be kx. I like to do them with just kx because that's the way we see them most often in the IB, but they do work for kx plus b. So the derivative of e to the kx, I'll go through this first one slowly. Our glob is the kx. We know the derivative of e to a glob is just e to that same glob. So e to the kx times the derivative of the glob. The derivative of kx is just k. So we can shortcut this to just say the derivative of e to the kx is k e to the kx. So that's a nice shortcut to use to save you having to do the chain rule each time. I'm going to skip the natural log one, and I'm actually going to come down to these two trig ones. Okay? We just used the sine kx one, and we saw that that was k cosine kx. Again, just using the chain rule. If it helps you to do the globs to prove this one, please go ahead and do that. Okay? The derivative of cosine kx, that will be negative k sine kx. Okay? Again, the negative coming from the derivative of cosine, the k at the front coming from the chain rule. Okay? This ln x1 is kind of interesting, or sorry, ln kx. Okay? So the derivative of natural log of a glob, okay? That's going to be 1 over the glob, so 1 over, in this case, kx, times the derivative of the glob, which is just k. Well, if we simplify this, we get kx over k, which just simplifies down to 1 over k. 1 over x. So those are just nice shortcuts to know going into your IB exam. You definitely don't have to have them memorized every day, but as you're revising and getting ready, those could be good things to have. All right, underneath here we have some quick examples. The derivative of tan 8x. Okay, I'm going to change that from a tangent function actually to a cosine, which we don't really see tangent functions at standard level. We can use the rule in the green box to just say the derivative here is negative 8 sine 8x. Okay, so that chain rule is just popping that 8 out in front because that's the derivative of the 8x. Same with the e to the 10x, derivative there, 10 e to the 10x. y equals e to the negative 14x plus 2. Again, derivative goes in front. That's the negative 14. E to the negative 14x plus 2 stays the same. That's our glob. So as you can see here, I'm not really doing the globs anymore. I'm hoping you've kind of got the idea of the chain rule, or at least are able to use these shortcuts. We'll do a bunch more derivatives here. We'll mix up the notation on the next one. We'll go dy dx. Same shortcut because we've got that linear glob up there. The 2x is our glob. So the derivative of 2x just comes down in front as 2 e to the 2x. The next one is not linear, so this is where we do need to be able to do the full chain rule, not just these shortcuts. Okay? The derivative of y equals e to the x squared minus 3x. We've got that glob is a quadratic, so it's e to the glob, we leave the glob alone, times the derivative of that glob, which would be 2x minus 3. Okay? You can leave your answer like that, but again, I would recommend bringing this polynomial piece to the front and leaving the e to the x part towards the back. Okay? But as you can see, this chain rule, once we get the hang of it, pretty easy to apply and usually 1 to 2 steps. Question C, we move on to what looks like a quotient, and we may dive for our quotient rule, but we can actually get around the quotient rule here by just rewriting this thing with a negative exponent. Okay? So that square root in the denominator, we can rewrite that as to the negative 1/2. And then it's just a simple chain rule rather than having to mess with the quotient rule to get the derivative. So the derivative of the outside, that's the negative 1/2. So we'll have 3 times negative 1/2. We'll leave the glob alone. We'll drop the exponent down by 1. So negative 1/2 will go to negative 3/2. And then we'll multiply by the derivative of that glob, which is just 2x. If we clean this up a little bit, we will have 6x over negative 2, and then x squared minus 5 to the 3/2, getting rid of the negative exponent. And finally, we can simplify this down a little bit to give us x over negative 3, x squared minus 5 to the 3/2. And while that derivative is perhaps not the cleanest or the simplest thing, it's a lot easier to take the derivative that way than it is doing that quotient rule. We can apply the same idea on the next problem. We've got a cube root squared. If we were doing this without exponent rules, we would have to do 2 versions of the chain rule. But a little bit of algebra rearranging at the start allows us to turn this into a single power 7 minus 5x all raised to the 2/3. From here, it's just 1 round of chain rule with our glob inside there, and then g prime of x, bring exponent in front, leave the glob alone, drop the exponent down, and don't forget to multiply by the derivative of the glob. Little bit of cleanup to come through here. This is negative 10 over 3 times this parenthesis to the power 1/3. So we're really showing the clean nature of this chain rule once we get the hang of it, but we haven't really got into why it's called the chain rule and where the chaining comes in. It seems like right now we're just doing a derivative times another derivative, almost a bit like making a product. Okay? We know it's not a product rule, but it feels like it's just a product. Well, this final example E here, a much more complicated derivative than you're likely to see at SL level, should allow us to really see why this is called the chain rule. Okay? So we're going to rewrite this function, just putting the cubed on the outside rather than tucking it on the inside of the cosine there, just to give us a sense of how this composition is being made. So the question here is, what is the outermost function? The outermost function is the cubing, so we'll start by putting the cosine ln 2x as our first glob. And now to get the derivative of f of x, we start peeling layers off the onion. Okay? So we start with our first glob of that cosine ln 2x function. We drag the 3 in front, we drop the power down, and then we leave the glob on the inside here alone. So we leave that cosine ln 2x alone. knowing that we still have to multiply by, and I'll use the operator notation here, d dx, we still need to multiply by the derivative of cosine ln 2x. Okay? So essentially, I peeled the cubing layer off at this point. Okay? This first part of my equation over here, underlined in yellow, this is done. I don't need to touch that. Okay? My work is on this next derivative sitting at the back. Okay? So I'll make a new glob here. My glob would be the ln 2x. Okay? Again, I'll just take another layer off of the onion here. So 3 cosine ln 2x squared times derivative of cosine of a glob. Well, that's negative sine of that same glob times the derivative of that glob. So times, in this case, ln 2x. Okay? And I just fill in that glob again with the ln 2x. So my derivative is getting a little ugly here, but I am peeling back layers of this composition. My first two pieces are now good. I'm going to clean them up in a minute. And I'm left with my final glob, which is this 2x. Okay? So my final derivative, I'm going to bring the negative to the front. Okay? I'm going to tuck the squared back on the cosine to save a parenthesis. I'm going to remove the glob on the sine ln 2x. And then the derivative of ln 2x is 1 over 2x times the derivative of 2x, which is just 2. And I can cancel these 2's out. For one final cleanup, I'm going to bring the 1 over x to the front to give me negative 3 over x cosine squared ln 2x times sine ln 2x. So this example features 1, 2, 3 rounds of chain rule. Again, much more complicated than you're likely to see on an IB exam, but it really gives us the idea of how these derivatives are chaining on the back of our expression as we pull layers off that composition. All right, if you made it through that example, we can finish before our IB problems with one of these conceptual ones that we've seen throughout our product rule and chain rule work. So we're told here that h of x is f open circle g of x. Again, my first piece of advice is always to rewrite that, make it look like a composition. This is f of g of x. I want to see that g of x inside the f of x function. We're given a bunch of values. We're going to make sure we use all those as we go through the problem. And we're asked to find the equation of the normal line at x equals negative 2. So we know for a normal line, we need two things. We need a point, and we need a slope. Okay? We're going to start with the point. It has an x value of negative 2. The y value will come from h of negative 2. This is a simple composition. It's feeding one function into another. It's not really calculus. Okay? G of negative 2 was given to us up here. G of negative 2 is 4. So this turns into f of 4, which was also given to us. That was 5. Okay, so our coordinate here is negative 2 comma 5. The slope requires us to find the derivative. So we need h primed of x. This is where we have to apply the chain rule in a conceptual manner, so we can use what we wrote in the red box earlier, or we can go back to our definition and just kind of glob up the g of x as our inner function. Okay? Either way should work. We want the value of the derivative at negative 2 to give us the slope of the tangent line. Good little check coming up here if we have all these values. That's a sign we've done this right. F primed of g of negative 2. G of negative 2 is given to us as 4, so that's f primed of 4. G primed of negative 2 is given to us as 2. You can put that in green because we just used that. And this lines up nicely that f primed of 4 is 8. So 2 times 8 gives us 16 using all of the values. We always love that when that happens in a problem. This is the slope of our tangent line. Okay? We know we need the normal line, so we're going to opposite reciprocal that. So our slope will be negative 1 over 16. Finally, we're going to build our equation of our normal line. They don't specify a form, so we'll just go point slope form. y minus 5 equals negative 1/16 x plus 2, and that will get us 5 to 8 kind of marks on an IB exam. All right, we now move on to a couple of IB problems. We're starting with a paper 2, so calculator allowed. They give us a graph of e to the negative x squared, and they label some points, A, B, C, D, and E. Tell us 2 of these are points of inflection. We're asked to identify those 2 points of inflection. Well, hopefully you know what a point of inflection looks like. It is where the graph changes concavity, and visually that would be B and D. If you're not up to date on your points of inflection, please feel free to go back and watch my previous video on that. Part B, we're asked to find f primed of x, the derivative. So our calculator doesn't help us here, as we actually need the function for this. Okay? It is a chain rule because we have the negative x squared up in the power of the e to the x up there. So we'll apply our chain rule. E to a glob is e to that glob times the derivative of that glob. Derivative of that glob is negative 2x, so we'll clean this up to say negative 2x e to the negative x squared for our first derivative here. Second part of this question is to show that, so they're giving us the answer. We're asked to show that the second derivative is 4x squared minus 2x e to the negative x. Now, in order to take the second derivative, we need to apply a product rule, because we have negative 2x times e to the negative x squared. So we'll get all of our ingredients for our product rule together. Our u is negative 2x. Our v is negative x squared. We've already taken the derivative of e to the negative x squared. We know that's negative 2x e to the negative x squared from part B, part 1. And then u primed here is clearly negative 2. We'll crisscross this over as we go to our product rule template, and we will arrive at our second derivative matching up with theirs, hopefully, once we've got our 4 parentheses, and we'll fill these in. Negative 2x times negative 2x e to the negative x squared, e to the negative x squared times negative 2. This should give us 4x squared e to the negative x squared minus 2 of those e terms, and to make it match theirs, we will factor out the e to the negative x squared at the back, giving us 4x squared minus 2 to complete our show that. Part C asks us to find the x coordinates of each point of inflection. We can do that either with or without a calculator. We know that the points of inflection occur when the second derivative is equal to 0, so f double prime of x equals 0. We can solve what we just showed equal to 0. Zero product property tells us one of these 2 pieces of the product must equal 0. If you know anything about e to the negative x squared using the above graph, it's clearly asymptoting on the edges, not actually touching 0. So we can say e to the negative x squared will not equal 0, and we can just solve this quadratic equation here. So that solves to 4x squared equals 2, x squared is 1/2, x equals plus or minus the square root of 1/2. They only asked us for the x coordinates, so those will do just fine right here. If you want to solve that using a calculator, this is a good place you might use your numerical solver. Okay? So we can just dive straight in with this equation right here on the right, not even worrying about the zero product property, and ask our calculator to do it for us. Okay? So on the TIN spire, we can go n solve. We can type it in just like it looks, 4x squared minus 2. Okay? And then we have times e to the negative x squared. We want all of that to equal 0, and we'd like to solve for x, please. And it'll spit this out for us, which is simply the decimal version of the square root of 1/2. And we'll check that right here. Same decimal. Okay? Clearly the graph is symmetric, so we can get the same result on the other side. IB would take either exact or decimal here, given that they don't specify. Final part here is to use the second derivative to show that one of these is a point of inflection. Right? All we need for a point of inflection is a second derivative equals 0 and a change in concavity. The easiest way to show the change in concavity, that's going to be with a second derivative number line. We'll put our 0.707 on here. We'll label this f double prime, and we will calculate the second derivative of two values, one on either side. So we'll do f double prime of 0 and f double prime of 1. This is a good place for the calculator. So that is 4 times 0 squared minus 2. You could probably do a lot of this in your head. Times e to the negative 0 squared. It's going to come out as negative 2. So on the left side of our inflection point, we have positive concavity. That's the plus. Okay? And we can redo all of this with the 1 on our calculator. Change all those zeros to 1s. And we get 0.735. Again, we don't really care about the value here. We just care that it's positive. Oh, sorry, negative on the left, positive on the right. I wrote the wrong symbol there. This is sufficient to show we have that change in concavity. Change in concavity, meaning that that x value is a point of inflection. And that completes this example. Okay, we have one more IB problem in this set of notes. Again, it's another paper 2, so we'll have our calculator handy. And we are given this function right here. We are told f of x is e to the 2x cosine x. Part A is a nice simple derivative they want us to show. So we'll get our product rule out again here because it's e to the 2x times cosine x. So our u is e to the 2x, our v, that's going to be our cosine x. We'll get our ingredients ready. Derivative of e to the 2x, 2e to the 2x. Derivative of cosine x, negative sine x. We'll glue all this together in our 4 parenthesis template. This is e to the 2x times negative sine x, and then cosine x times 2e to the 2x. We can simplify this by taking our factor of e to the 2x, and it's very easy to see we have 2 cosine x minus sine x, just like they told us we would need. Nice simple show that to get us going. If we aren't able to get that, we're still able to carry on the rest of the problem using their result as we go. Let L be the normal to the graph at x equals 0. Find the equation of L. Okay, equation of a normal line. We've already done that in this set of notes. Okay, so we know for part B we need a point. The point will be 0 comma something, and we need a slope. Okay. The point will come from f of 0. F of 0 is e to the 0 cosine 0, which is 1. So the point is 0, 1. The slope we're going to get from f prime of 0. We could use our calculator for that bit. We can just substitute in. That's e to the 0, 2 cosine 0 minus sine 0. You can use your calculator for any of these calculations if your trig is not quite as strong. This should give us 2. This is the slope of our tangent line, meaning the slope of our normal line will be negative 1/2. Putting all this together, we have our equation of our normal, y minus 1, negative 1/2, x minus 0. Now technically on part B you can leave your answer like that, but given you've got this 0 here, I would highly recommend you rearrange this to slope-intercept form. That's going to help you with C part 1 as well. All right, for C part 1 here, we're asked to find the x-coordinate of point P, which we're told is the second intersection point of this tangent line and the original curve. So this is a great place to bring the calculator in, either nsolve or a graph. I'm going to go with a graphing approach here so we can see what we've got going on here. So we'll add our graphing page. Okay, we're going to graph the original function and our tangent line. Our original function is e to the 2x cosine x. Make sure we're in radian mode for this. Okay. And we are given a domain, so we're going to set up our window to kind of match that domain so we're not seeing anything extra. We're told we're on the domain -1 to 2. You see a nice piece of graph right there. We're going to put in the equation of our tangent line, which we just found. That is -1/2 x plus 1. So we'll put that in here, -1/2 x plus 1. We see that first intersection point on the y-axis, which we were told about. Our second intersection point is over here. So menu, analyze graph, intersection. We'll drag over that, and we'll get our solution here, which is x equals 1.56. Okay. This completes as far as we're going to go on this problem for now. The remaining part tells us to find the area enclosed by a graph, which is you're going to use integral calculus. So we had right at the top that we were going to omit that part for now, but it's quite easy on the calculator, and we'll get to that in a future video. So this completes our work here on the chain rule and actually all of our derivative rules to this point. So we now have the ability to take derivatives of products, quotients, and composite functions, and even combinations of those. Okay? So in the standard level course, we have learned all the derivatives we need to at this point. And we're going to wrap up Unit 6 in the next section with one little application, which is called optimization. Again, if you found the video useful, please subscribe to the channel. Go ahead and like the video, leave any feedback, comments below, and I look forward to seeing you for that next lesson.